about 1 every 10 seconds or so joining in, but we will get started. Welcome today to the European Workshop Week from EPRI, historical now event that we've been holding every year, sometimes in person, right now remotely. We look forward to getting that back together in person, likely next year. This session is called Advanced Analytics for Wind and Solar Assets. We have a couple great guest speakers as well as a couple EPRI leads here with us today. My name is Brandon Fitchett. I lead the wind energy generation focused research here at EPRI. We also have Michael Bullen, who introduced himself in the chat, leading the solar generation research. And Ron Schoaf will kick us off here. I'll let Ron introduce himself in a minute. Again, thanks for joining, everybody. We are here. This is a workshop, not a spectator sport. I like that comment. So feel free to speak up, put questions in the chat. We'll all be watching that. Feel free to unmute yourself. I believe you might have that capability, and pause us. This is a collaborative effort here. We do have some presentations ready, but that's not the main point of this. I'd say it's about 50-50, content, and we'd love to hear your feedback and your ideas. We will be asking you questions throughout, and we will be monitoring your questions in the chat, as well as your ability to come off mute and just talk to us. This is what we'll go through today. Again, Ron will kick us off. We have some great presenters I'd like to thank for being here as well from Enel, Federico, thank you, and Asger from DTU, as well as Michael and myself from the Wind and Solar programs at EPRI. Raja Pulikolu, our principal technical lead in the wind energy program. Daniel's introducing himself in the chat from the solar side of things as well. And a couple of our colleagues, Yichao Liu and Iman Lenoy from EPRI Europe, will introduce themselves when we get to them as well. So thanks again, everybody, for being with us today. So right now, I'd like to turn it over to Ron for some opening remarks, introduction to himself and some of our research in the generation sector, especially around analytics, energy transformation, and digital transformation. I'll pass you the ball here, Ron.
Thank you, Brandon, and thank you, everybody, for joining our event today. EPRI has been engaged in research for 50 years now. This is our 50th anniversary, and we have been engaged heavily in R&D across the power generation value chain in Europe for quite a while as well. We're pretty deep into the energy transformation, and in Europe, you're deeper than most countries and regions. So that a lot of the things we're going to discuss today are not just conceptual, but they are the reality that you're living on a day-to-day basis. We see opportunities to improve the operations, the reliability, the dispatchability of our renewable assets. And we believe that digital transformation represents a series of technologies and approaches that can enable that effectively. So a lot of what you'll hear today is focused on those items. So as I go here to this next slide, we see some key challenges that have played out throughout the energy transformation, including the increased need for flexibility. Now that happens to manifest very early on in thermal assets that are trying to balance out perhaps some variability of the renewable assets, but we also see the need in mature systems with higher levels of penetration of renewables, that those assets need to be flexible as well. That's always been true of hydro, but wind and solar are increasingly being relied upon to provide not just grid services, but a flexible output, which drives us towards all kinds of different design and operational choices, including the integration of energy storage, more controls over the inverter, and other data-related controls options as well. We see that resiliency becomes increasingly important. We have just had a workshop yesterday, in fact, focused on power system resilience and the resilience of energy supply assets in particular. And what we have noted through events around the world, climate change is presenting us with new and more frequent challenges on an ongoing basis, whether that be unseasonably cold weather in places where you wouldn't have expected it, or extraordinarily high winds that may create damage, or wildfires, or all kinds of very difficult scenarios that present opportunities for us to improve the ability of our energy supply assets to manage their way through and to still produce power through those very difficult times. The integration of renewables has been a critical challenge, but again, as we go forward, the integration of energy storage and the dispatchability of those assets is becoming increasingly important. We know every energy supply operator is tightening their operations and maintenance budgets. Of course, it's an increasingly competitive market, and thin margins, make or break the profitability of assets. So, tightening those O&M budgets is critically important, and we know that there are opportunities to do that in a very intelligent and focused way by gathering data, understanding what that data means in terms of the asset performance and health of our equipment, and how that may compare to information we have from other operating assets. So our ability to intelligently tighten our O&M budgets while still achieving high levels of performance and reliability, that represents both a challenge and an opportunity. We see increasing environmental regulations, whether that be related to wildlife impacts or whether it be related to end of life, recycling or circular economy based effects. We know that those requirements are becoming increasingly stringent. So on the digitalization side, we see that data quality, the ability of us to have high quality, valuable data is critically important, right? The data is the most valuable asset that we have, next to maybe the physical assets that are producing the energy. And so if we have good, solid data that can be acted upon, we're in good shape. Information protection, cybersecurity is critically important. Obviously, we're encountering some very difficult geopolitical times right now, but there are other drivers for the need for information protection as well. And having good cybersecurity posture is critically important. Our ability to analyze and use the data to drive decision making at the asset owners is important. And we find increasingly, especially in renewables, our ability to compare data from an individual owner or their individual assets to a peer group across the industry, in what has been a pretty competitive environment, adds a lot of value so that you can contextualize the data that you are seeing in context of experiences that others have faced. Again, enabling you to make better decisions as we go. And collaboration is what drives that. And that's really at the foundation of what EPRI does. We know that the data piece has a real role to play here and provides a lot of value. And I think we'll dive very deeply into all of that today. But we don't want to lose sight of the fact that you can't just add fancy software and data tools and expect good things to happen. We know that as asset owners and operators, you are focused on outcomes, that being performance, reliability, resiliency, operational efficiency, and security. So in everything that we do not want to lose sight of the outcomes we're trying to achieve that the data tools are meant to enable. So for us, it's a symbiosis. We need to ensure that our assets are performing as well as they can, that our teams are performing as well as they can, that our system is secure and reliable, but that these data tools are capable of enabling even better performance as we go. So with that, I think today we have an excellent workshop so we can dive deeply into specifics of how we approach these research problems from both a solar and a wind perspective. I thank you for your attendance. I appreciate your engagement, and we certainly look forward to engaging with you more and more. A couple of us, in fact, will be in Spain in a couple of weeks for the Wind Europe conference, so maybe some of you will be there as well, and we can chat more in person. So Brandon, I will pass it back to you to take us into the next stage of our workshop today. Thank you.
Ron, excellent overview. We're doing a lot of things in our power generation R&D sector. And again, like Ron said, today we're going to dive deeper into the wind and solar aspects of analytics, the importance of the different data sources that are out there, what we can use that for, performance, reliability, and health monitoring of these assets. And again, I'm from the wind side of things. There are a lot of things we're doing across some of these other types of assets where the challenges are getting the data streams, producing the data streams, monitoring health. For now, what we're finding in wind and sometimes in solar is that some of the challenges is using the data that we have already. There is a lot of data. These are digital assets, smart inverters, condition monitoring systems, vibration monitoring systems. kilohertz resolution of a lot of these data streams, kilohertz, 1 second, or 10-minute average data. What can we do with all of this? So we're going to talk about this today in a wind and solar sense. In the wind breakout, we'll get into some of these more details, what we're going to do here, and what's possible. And we'd like to hear from you about where are your challenges in accessing data, and then applying analytics to that data. And again, from the wind side of things, so again, we'll get deeper next up in the breakout sessions for wind and solar. But for now, we'd like to hear from one of our guest speakers, and this from mostly the solar side of things, from Federico from Enel. I would like to welcome you and thank you for being here with us today, sir. I know you have some solar insights to share with the group. And if anybody, again, has any questions, please put them in the chat for the EPRI or for our guest speakers here. We're a very collaborative organization, hold a lot of roundtables and open discussions, so don't hold back. And again, thank you for being here with us, Federico. We'd love to hear what Enel is doing here in some of your solar analytics aspects, and feel free to highlight some of the challenges along the way, sir. Thanks a lot.
Okay, thank you too for the invitation. I will take the control of the screen in order to share mine. Let's see.
Sure, let me make sure you can do that.
One moment. Let's see. Share. Is it possible for you to view the screen? I'm sorry. Is it possible?
Yet. I don't see it yet. Do you have a share button at the bottom, or you did that already?
If there are... yes, I want to share. Share.
Now we see it.
Is it possible?
Yes.
Oh, perfect.
Looks good.
Okay, so let's start with our journey in what we call the solar data-driven maintenance. 1 minute to introduce myself. I am Federico Argenio from Enel Green Power. I am responsible at worldwide level for data analytics. I am 40 years old. I am a mathematician, specialized in pure mathematics. I am very lucky because I'm leading a team of 15 persons, mixed between engineers, mathematicians, and so on. We growed in a lot of years in Enel generation, and we are expert in this kind of topics. We cover the entire value chain of Enel, from business development to O&M, passing through engineering and construction. But today we will focus on our development in terms of solar data-driven maintenance, how we translate solar data into value for Enel. I think that every one of you knows what is Enel. So, but here I want to let you focus on what is the biggest problem of managing through data solar fleet. Here we are speaking of a word that is a lot of it's very much not standard, integrating technologies and different data sources from different countries. Here seems that at first view seems that managing a solar plant is less complicated than managing a wind farm because the solar component are very simple. It's a machine that is, in a certain sense, is not a machine. It's something that is electronical linked. So here seems that it's much more easy to manage this kind of technology. The answer is that at least it's comparable because what you get from a wind turbine is something much more structured than a collection of weak signals that you can get from a solar plant. Here it's important in order to understand the magnitude of an L. Let's think about our record in terms of production for the entire fleet. That is like moving my entire country for one day only with our generation portfolio. So it's a big result because we are speaking of a country of 60 million people. Here we have the technologies that we cover, and here it's important to understand what means working with this technology, because the classical approach to data-driven maintenance is more linked to wind, geothermal, thermal, or hydro fleet, because here you have components that are, or main components that are rotating. So in a certain sense, you have a lot of sensors that are able to anticipate or to better improve the production of your machine. Here, the problem is much more difficult to approach, because here you have a collection of data that are mainly electrical. You do not have anything that is rotating, so working with temperature obviously is something useful to understand if there is something that is underperforming, but keep in mind that you do not have the intelligence of a wind turbine in order to absorb the effect of the temperature in the production. So then the other complication that you have there is that normally you do not have a one-to-one correspondence between the inverter and the tool to sorry, Dani, sorry, because I'm not alone at home and it's not so easy. You do not have a one-to-one correspondence between the inverter, so the generating unit of a solar plant, and the resource measurement tool, like something to measure the irradiance. So here the situation it's a little bit more tricky. And also the SNL, we have realized some solar plant that are very, very big. For example, think that 1 megawatt installed capacity of solar plant is more or less 2 hectares of terrain. Think that we have plants of 500 megawatt in Mexico. So the extension to cover is it's very, very big, and you have to deal with signals that are that you have a magnitude of signals that are 100,000 different signals for every plant, that every signal is covering a small portion of the attainable production. For example, I think that a fuses in a string can cover something like 6-7 ampere. So if you want to manage this stuff, you need something very clever to do this. The other colleague in the previous speech told that it's very important to us, that it's very important to have the capability of managing the data and understanding the insight that this data have. It's something totally true. For a person like me, working in this world is like working in Disneyland every day, because think that our fleet is producing every minute a book of more or less 3,000 pages. So here I am fascinated with Lord of the Rings. I hope also you are. So every minute we are writing an equivalent of the Lord of the Rings with the data of our fleet. In order to do this, we have realized, mainly dedicated to solar, we have this solution for all the other technologies, but today we speak about solar. We have released a solution that we called the Solar Performance Analytics Suite. This solution is something that we developed and consolidated. We developed in a couple of years of job and consolidated in 2021. This solution is something that for us is a great goal, because from Rome we can remote monitoring, not control, monitoring our entire fleet from the SCADA data through the data quality system to the analysis of normal behavior of the different generating unit, and the possibility of analyzing the root cause of underperformance. This stuff is distributed in all of our countries that are 14, in which the solar plants are present. And it's something that is used by 100 person during the day, that analyze results or provide information to the platform. Was a great effort by great collaboration between our technical line and our digital line. Let's see some details about the tool that we have in our at our disposal in this platform, that is very, in my opinion, is very interesting. So let's start with now the name of the tool was decided by me for some tools, and by my colleague Angela for other tools. That Angela is very romantic, so in my opinion it will be easy for you to understand which name I was chosen by myself and which one by Angela. Let's start with some insight. The first tool that we developed was named Icarus. That is a tool dedicated to what we call the operational efficiency. It means the control, the remote monitoring of our solar fleet through the analysis of what we call the power curve of the inverter. It means that for every single inverter in our fleet, we developed a model based on neural networks that is able to get data from SCADA about irradiance, temperature, power, and so on, and calculate the optimal behavior of the generating unit. Then, by getting the data from the field, is able to calculate if you are losing production, and using the intelligence of the SCADA and some algorithm developed by us, is able to create for you a root cause analysis. This stuff, it's very important because allow the person in on field to do to perform a data-driven maintenance based on the impact of the different event. The second tool that we created was named Speed Alert. This tool is something that is related to an aspect that is a property of the solar technology. One of the weakest component of a solar plant is the pyranometer, so the sensor to measure the solar radiance. Weakest means that is required with a certain during the year, with a certain periodicity, is required to recalibrate it to assure that it works in a correct way. We created an algorithm able to monitor the different pyranometer on field and to detect the different causes of abnormal behavior of this sensor, so that the person on the plant can do a precise maintenance and a precise recalibration of this sensor. Then other tools for which I am very proud are the string monitoring, that is something that we use for central inverter. It's the central inverter. It's a big inverter that for a cost opportunity, it's not required to have a one-to-one correspondence between current measurement sensor and single strings. This stuff is very useful for very big solar plant, for which installing 100,000 of sensors obviously cost too much in terms of installation and maintenance of them. So we created another algorithm based on neural network that is able to isolate a single string failure for the different inverter, and allow our colleague to go to do a dedicated maintenance to this only to a certain portion of the plant and not in the entire one. We reduced the time for detecting string failures by a factor of 5 with this in terms of time. Then some other applications that are very, very nice, in my opinion, is the sunflower tool. That is like the sunflower, there are solar plant equipped with tracker system that is a system that allow the panels to follow the sun during the day. One of the problem that this system has is the possibility of miscalibration. That means losing production. So we have developed an astronomical algorithm that allow you to create the perfect behavior of the tracker, and by overlapping this behavior with the current one, you can detect a miscalibration and address the maintenance. Then we have our robot management platform, our ROMAP project. This is a tool that we developed with drones flying onto the solar plant, equipped with a thermal camera. And we developed a model based on convoluted neural networks, so an example of deep learning for image recognition, that is able to detect failures or problems to the different panels, like, for example, hotspot, or, for example, bypass valve that is activated, or troubles also there to strings, and so on. The last tool that we developed is something that is something very classical in solar technology. It's a sort of repository in which our colleague can store from the field the different analysis based on HIVU curve or ultrasonic analysis and so on, and we have some algorithm able to detect outliers and stuff like this, able to detect if there are problems to the panels. Our challenge for this year are, if you have if you understood what I was explaining, you should for sure you have understood that we were much more concentrated in anomaly detection than in predictive analytics. This stuff is something that we are developing now for certain kind of inverter. The reason it's very easy, simply that our fleet is very dishomogeneous, so it's not easy to find a methodology for predict, for example, inverter failures without the construction of a database of anomalies. This is from mathematical point of view, the best output of our solar performance analytics suite is the construction of this database that finally we have, and now we are able to calibrate the model. So this will be our challenge in this year. I forgot to tell you that in the Icarus tool we have also a methodology dedicated to monitor the soiling of the solar panel in the plants for which this phenomenon is relevant, and this why we are monitoring the effect of the soiling, because we have developed an optimizer that based on market variables and stuff like this tell to you when is necessary to clean the panel in order to do not lose too much money from the market. So I think that I am in time. So Q&A for you all.
There you go. That was great. Great overview of how you're monitoring solar plants. There are a couple questions in the chat here. I'm going to ask one first that I had early on, and it's how do you, are there challenges, and how have you overcome challenges in, let's say, integrating the data that you need, integrating the data that you need to do these analytics from a highly variable fleet in terms of configuration, especially on solar, where you have different manufacturers of inverters, different manufacturers of trackers. How have you overcome some of those challenges in a general sense of integrating very highly variable configurations of plants into these centralized analytics?
Yes, this was one. Meanwhile, I was reading the question in the chat because, sorry, but sharing the screen, I was not able to read the question. So I will answer to your question, then to the other one brought in the chat. This challenge that you are proposing was was one of the hardest. We developed a system of metadata. So it means that for every solar panel, every solar plant, or more specifically for every inverter, we defined a sort of golden record that is a vector with all of the dimension standardized that this inverter must have. Then we created a stratum with the operation is named ATL, extraction, transform, and load. We created an ATL between the SCADA and our central system that allow us to homogenize all of the data for the different manufacturers. The variables that we use are not a secret, are something very classical, like electrical ones or ambient environmental measures, both from DC and the C side of the inverter. Then, first question, are these tools available for folks to use outside of Enel? I am not the right person to answer to this question. We have a commercial department. I think that they will be happy to hear this question from you all. From my point of view, the system can be adapted to every SCADA. It's a matter of having the description or having a disclosure in the variables that are inside the SCADA of the manufacturer. We are lucky that we are covering something like 20 different manufacturers. Then neural networks and physics-based model. Who asked for this question knows exactly how to do this job. In fact, my approach, that in my opinion is working well, then everything can be made better. But in my opinion, this stuff is working well. Is start exactly from the physics of the machines, then isolate all of the phenomena that can be isolated with physics, and then apply machine learning and so on to the residual part. An example, very stupid, is that for detecting troubles in terms of set point to the inverter from the TSO, we use only the producible and the TSO set point, no machine learning there. But if you want to understand if an inverter is suffering problems in terms of ice or snow, here is necessary to know how to deal with hidden path recognition. Then last question is referred to the data quality assurance and the curation performed to feed this tool. Here we have a system that the data quality in NL we are very it's very important for us, the data quality. So we have two levels of data quality assurance. One level is dedicated to the real-time control. So here the different countries that we have in our portfolio are performing a data quality check based on a central directive, a central approach. Then all of the post-processing, data quality in post-processing is performed by our tool. For example, we check if the data are out of certain threshold. We check if the data are missing respect to the number of occurrence that you must have if you analyze 1 hour of minutal data for power output of an inverter. We check the coherence of the different data in terms of, because a problem of these sensors, especially in during if you have a problem in terms of voltage and stuff like this, is that they can stop and send to you every time the same value consecutively. We name this stuff frozen data. So we have a detector for frozen data and so on. Then, if it is possible, for doing the post-processing analysis, we reconstruct this data using, for example, info provider for the ambient temperature or satellite data for the irradiance. If it is not possible, we have a system that will send an advice to the plant supervisor asking to him why all of these data are missing, because obviously there are some information that the SCADA system cannot catch. For example, 2 years ago, or 3 years ago, sorry, we had an earthquake in Chile involving some of our wind farm. Here, obviously, the wind farm does not have any signals in the SCADA saying there is an earthquake. But what you will see is a lack of data. So, using this advice, the supervisor communicated to us that there was an earthquake. I think that all of the questions was answered by me. Are there other questions? The thing for which I am most proud is that everything was developed by us. And that is a marvelous result. And I am not happy that I am there alone to explain this stuff because the person in my team did a great amount of job. Thank you for giving me the possibility of participating to this event. Thank you.
Thank you, Federico. You did a great job answering the questions. Great knowledge base, we can tell, on the solar aspects. Great ideas here. Great data checks. I think that was really important answers to the questions about data quality. You know, you can't get good analytics without good data, and the data from the field isn't always good. So,
garbage in, garbage out.
Yes,
to be polite.
It's very true with wind and solar, or almost anything you're trying to analyze. And you know, some of even the specific ideas, you know, frozen data is something that throws people off all the time. Frozen data or linearized, you know, connecting two disparate data points with a line, you know, in a database, that happens sometimes too. So yeah, very, very good ideas there on everything you should be analyzing on a solar farm. Great job, great insights.
Thank you.
So with the warm up, you know, getting some great insights about the current status of state of the art, really, of solar monitoring, some of the industry leads in monitoring solar assets. We are going to move towards a breakout session here in wind and solar. So I'd like all the attendees to be ready. You will, I think, have to choose a session here. Choose a wind session or a solar session. I am going to, I think Robin, you may have to launch these here. I don't have the button available on my end. And I do see I am able to join the wind session, so I'm going to hang out here for 1 second, but I'd like everybody, all the participants, if you're listening, to join a session. If you know, we see people not joining a session, maybe a signal to who's paying attention. So I do see people joining the solar session. I'm going to join the wind session in a second. You may hear it quiet if you come back. I'm going to leave a little note in the chat if somebody is stepped away for a second. And in the wind session, we will go through and ask you, actually, poll the audience a little bit about some of the opportunities and challenges in wind and solar analytics, and we'll have some things to share there as well, especially on health and performance and reliability monitoring of these types of assets. So thanks again, everybody, for joining. We'll see you in a minute in the breakout sessions. These will last for 30 minutes, and then we'll come back here and regroup in the main room to discuss some takeaways, as well as some future applications and future opportunities in Europe for analytics and working collaboratively in general. The wind session's looking popular. Solar session, if anybody's interested in solar, need some attendees to the solar session. And there's about 20 people or so who are not yet in a session. So wake up, and we'll see you in a few minutes.
Hey, Robin?
Ron, I think Robin might be in the
Oh,
other parallel session just as it kicks off.
gotcha. I don't know if folks need assistance with figuring out how to get into the breakout session since we still have some here in the main meeting. But under the participants tab, there should be a little button at the top that says breakout sessions. If you click that, you can then join either of the breakout sessions based on your interests.
And I just put some guidance in the chat. So room 1 is wind and room 2 is solar.
a lot, everybody, for joining the breakout sessions. Michael and Danny, is the solar team back in the solar breakouts?
Yeah, I'm here, Brandon.
We definitely ran out of time, so appreciate it. I just wanted to, I'm going to ask you, Michael, actually, to give a quick, 2-minute recap of some of what you went through in the solar breakout, and then Roger will give a recap of what we talked about in the wind breakout session. And then we're going to move forward into where we see some of these analytics applied in the future. In this case, we're going to talk about offshore wind next. So Michael, then Raja, and then we'll go into some discussions around analytics and offshore wind.
Sure. So I think most of our conversation was actually focused more on kind of the aggregation of solar and data to help inform some of the wires side, right? So from kind of a transmission operator perspective, right? How could you better understand the various bits of information and make actionable insights from that, right? So this is going even one step further from what Federico had mentioned from Enel, right? We'd have all those great insights that you could take within the plant perspective, but then it's now going to that larger fleet-wide and broader interconnection perspective of all these inverter-based resources onto the grid that are variable by their very nature, to then help figure out how do you make those types of system level insights. But maybe real quick, a couple of things that I could show though is, again, to build on, I think, some of the points that Federico had made and help inform high level understanding of this data, right, is that there are a few different forms of maintenance, right? Because a lot of these advanced analytic tools are really meant to help inform what you're going to do within a plant. And so there's ways that you could either work reactively, where something has broken and then you go fix it after the fact, or you could try to do preventative maintenance, whether based on some amount of time elapsing, or if there's a condition such as from sensors that you can then act upon. And that's where you would both focus on things that are critical, right, is where your preventative maintenance would focus, and things that are not critical, you'd allow to just move into this reactive break fix type mode. And this is part of the equipment reliability framework. And so, from a data analytics spectrum, I think, if you just have that sensor data, then you are more in a reactive time-based mode. But then if you can do some analysis and normalization of this data, you can perhaps do some more reporting on it. But then as you go through in fancier and more advanced techniques by adding models and algorithms, this gets into the fault detection mode that Federico had discussed, and more of this condition-based preventative maintenance that's enabled, right? All with this goal of reduced cost and downtime at the plant. If we start to learn from some of the fault signatures, you might be able to automate the diagnosis of what has happened, right? So this is going beyond just detecting something has happened, but now saying we know what has happened, we can diagnose the issue, and you might be able to even move into kind of a pre-fault signature mode where you can predict something is going to happen, and this kind of predictive maintenance and some of the other flavors that go even further than this are really what a lot of folks are still striving for. And given the nations of solar in general and the number of different manufacturers and vintages of technologies, there's going to be quite a bit of effort to get towards this kind of mode, this fault prediction mode. But it's certainly something that I think we could do as an industry by working together and collaborating. So I think that's one of the important messages that I certainly want to get across to everybody today. So, and we'd certainly be able to provide any additional insights on solar analytics. You can contact myself, Michael Bolin, it's mbolin@epri.com, or Danny Fregosi, who is our data expert. So dfregosi@epri.com, and we'd be happy to have further conversations on this topic. So back to you,
Michael. Great. Yeah, thanks a lot. Great overview of the solar breakout. And Raja, really, I saw you taking some good notes there during the wind breakout. You know, we talked both about, you know, some of the challenges and even compiling some of this data and why higher level strategies are necessary so that you can take and apply them. So Raja, go please give us a quick overview if you would. Thanks a lot.
Sure. Yeah. I'll just maybe quickly summarize into 3 bullet points, key takeaways in less than a minute. Number 1 is, during the discussion, John pointed out that digitalization, data collection, it doesn't need to be O&M group initiative. It has to be coming up from the upper management chain. It should be like a organization level initiative, not just specific small group of people working on it. So that should provide more visibility and provide more value at the organization level. And also, as Gar mentioned about data streaming, not only at the turbine level, but also the new technologies are evolving. So we should also focus on for example, the new technology data collections, floating structures. So we should add more data streams as we develop new technologies, and also think wisely about where to put the sensors, which are the critical components at which we need the sensors. So start thinking about it at the technology development stages itself before implementation in the field, so that operators have better health monitoring technologies in place. And also, number 3 is, what are the smart data sets that we need? So Brandon mentioned in detail about some of the key data sets that we need for reliability, performance, and health monitoring. So if anyone needs more information on that, we can have follow-up discussions. So that's my 1 minute quick summary, or maybe I took more than that. Back to you, Brandon.
No, thanks, Raja. Yeah, again, great overview. So, you know, now I think we are, after those breakouts, we're going to move into an applications-based discussion. You know, once we get this data together, how do we use it near and future applications? So we heard from Anel earlier on about, you know, kind of industry-leading state-of-the-art of analytics for solar. We're going to talk about now some research and that may be applied in a few years' time. Some government, you know, some EU, some European government-funded projects in offshore wind. And for that, I'd like to introduce a team here from EPRI, from DTU, EPRI US, EPRI Europe. We're now, you know, we're all one team now, in a collaborative effort with DTU and many other people. So we'll talk about a little bit about who that is in this project called Hyperwind and advanced analytics for wind assets, especially offshore. And I'll ask you to introduce that, Raja.
Sure, thanks. Can you please pass the controller so that I can move the slides?
Yeah, for sure.
Thank you. Thanks. So we have 2 great presentations. Asker is going to talk about the monitoring technologies, the physics-based models that he has been developing under the Hyperwind project on for the drivetrain applications. And also, Ichao is going to talk about how he's going to take the outputs from Asger's model, mechanical models, and put it as an input to his electromechanical models into the generator, and to study the impact of grid events and overall drivetrain reliability. So before getting into that, just want to give a quick summary on what EPRI has been doing under the wind program. So the work that we do is applicable to both offshore and also onshore wind fleet. And our work has been mainly focused on reducing operations and maintenance costs, at the same time increasing reliability, performance, and flexibility of the wind fleet. So we have been achieving these goals by working on 5 major areas, which we have listed on this slide. One is operational efficiency and excellence. Brandon, Ron, and others spoke about turbine digitalization and automation. That's the key, especially the new wind operators who are getting into the market. They need assistance in terms of collecting the smart data sets before they get the keys for the wind farm, so that right from day one, they are efficient enough to start monitoring their fleet. And then cost reduction, even Michael mentioned about application of this to solar fleet. So the principle is the same. The early that we detect the damage, then we can do more preventive maintenance, a low cost maintenance, a proactive repair, than a full system replacement. So for example, if you identify damage in a gearbox on a wind turbine in its early stages, especially in the high-speed shaft and intermediate shaft, then you can repair it maybe for 15,000 euros to maybe 60,000 euros, versus a full gearbox replacement. If it is too late to repair it afterward, then you're looking at a cost of maybe 400,000 euros, including parts, labor, and crane, etc. So the third bucket is maximize efficiency. The goal is to identify the underperforming turbines and fix those issues promptly before it's too late. So this may increase the production revenue by at least 200,000 euros at a typical wind farm. And also applying the same principles, same theory on environmental issues, like coming up with optimal curtailment strategies to reduce bird bat fatalities, and also material sustainability. And last but not the least is reliability and safety. At EPRI, we have been working with utilities and operators, getting their fleet reliability data into our web-based tool, which is Winner. To date, we have around more than 20 gigawatts of wind fleet data, and we have been mainly using this to come up with better health monitoring technologies, to come up with better operations and maintenance budget forecasting, and many other applications like supplier selections, etc. So in summary, combining all these technologies together, overall, we have been saving more than $1 billion per year at a typical wind farm for the operators. So with that said, I'll just give a quick overview of the Hyperwind and then hand it over to Asger. So in Hyperwind project, we have been working with multiple partners, DTU, Asger, and his team. They are leading it from the front. And the goal of this effort is to link the oceanography, wind loads, and then transmit those loads onto the main rotor, and then convert those loads into stresses on the individual components along the drivetrain, like gearbox bearings, main bearing, and generators. And once you have these local loads and stresses, how you can use these local loads and stresses to predict the reliability of the critical systems and components. And if you know the critical systems, then you can come up with better O&M strategies, reducing your overall O&M costs and LCOE. So at the high level, under Hyperwind, the goal is to reduce the LCOE by 9%, CapEx by 4 to 6, OpEx by 5 to 7%, and increase production revenue by 2 to 3%. So with that, I'm going to invite Asger to talk about how we are achieving these goals and where we are now. Asger, please take over.
Muted, Asger.
Sorry. Thanks. Okay. I was just asking how to shift the slides, but I guess that's this bottom over here. Yes. Good. Thank you. Okay. Yeah. So thank you for inviting me, as well as Dilibun here, who is postdoc working at DTU Wind Energy. So we paired this slides together. We will sort of just illustrate to you sort of the issues we have on how do we actually assess the, let's say, the life of a main bearing. If we know, let's say, the aeroelastic model of the turbine and are able to calculate the loads of the turbine, given that we kind of know the environmental settings of this turbine. Oh, sorry, that was the wrong way. So if I just illustrate a little bit more what Raja was explaining, you can kind of say that Hyperwind is starting with the mesoscale sort of atmospheric description of what is the atmospheric turbulence, what are the wind sort of phenomena we will see in the atmosphere. And in order to understand what that means when it comes to what is the loads acting on the different turbines, this is what we want to try to take into account in hyperwind. And from a, let's say, probabilistic viewpoint, try to describe this as if you have a certain number of turbines and you sort of place another turbine further down in the wake of the other ones, what you will sort of observe is that there is a huge disturbance of the wind due to the wakes of the other ones. And you sort of have to take that into account when you go from single turbine into modeling a wind farm. And of course, you can kind of say that is also implying an uncertainty on what are the loads actually on the different turbines in a wind farm compared to as if you saw them individually, which would be sort of the usual or the standard way of asking how to design turbines. Now, finally, we want to sort of mitigate what is happening of this interaction between the turbines into now, can we calculate using air elastic codes the loads acting on the blades? And now, of course, one of the questions is if those loads, when they're mitigated into the drivetrain, will this increase the chance that some of our components in the drivetrain will suffer from this? So one of the sort of scopes of work package 5 in this is trying to mitigate the rotor loads into the drivetrain. And we have sort of two cases that we're discussing. One of them is a Teesside wind farm operated in the UK by the French energy company EDF. This has been running like since 2013. It consists of 27 Siemens wind power 2.3 megawatt machines with a 93 meter rotor. And you can kind of say that the good thing of looking back into this relatively old farm is that we can compare now the track record of what has actually happened in the SCADA data, as well as sort of some of the condition monitoring data. And then we can try to ask ourselves, would we be able to sort of come up with a prediction of, for instance, what should the life of the main bearing be? And here we have sort of put some typical bearing specifications that you can all find if you just search for spare parts for these kind of turbines. So the relatively old turbine numbers or turbine models it gives more transparency into what is actually sitting inside these turbines. So this main bearing that I'll be sort of talking about is sitting just right here behind the hop. And this is sort of what we will investigate or have a look at today. But we do also have another case, which is the future floating wind farms. And I just want to remind you that there is this NREL report here of the 15 megawatt IEA reference turbine, which is a large floating machine. And the drivetrain for that one is not based on a gearbox as we have over here, but it's based on having a large permanent magnet generator with two big main bearings supporting this structure. But just to sort of get a feeling of what is it we need to do, well, the bearing, say, load-life relation is kind of looking as a graph so you could represent like this. So if you have the mechanical load on a bearing, on this axis here, and the number of cycles that this bearing will last before it fails, it will probably fall on this kind of line here, which is sort of less described by this kind of sort of a power law relation here. So if you measure a huge number of bearings and you were measuring at different load levels, you would find that they would kind of you would be able to probably fit a line to it that looks like this. But what the bearing manufacturers are then doing is saying, well, in order to ensure that 90% of all the measurements of the fleet or all the tested bearings are above the design line, we will sort of move the design line further down compared to what we fitted to the data. So you can kind of say that this is sort of the measured mean value, but you should imagine there's a sort of a normal distribution of the numbers, and now we're moving this down in order to get 90% of the measurement above and only 10% below. And this is ending up in a bearing life equation that looks like this. So you have sort of a dynamic rating coming from the bearing manufacturer, and then you have the dynamic bearing load. And if you also know the exponent for this, let's say, bearing kind of fatigue law, you can calculate what they specify as the lifetime of this bearing. So basically, this is telling you you can look up the specifications of the bearing from the bearing manufacturer, but you have to calculate this dynamic or bearing dynamic life. So just looking at sort of spare parts in motion, which are sort of web pages where you can buy spare parts for these, let's say, relatively old turbines, you can sort of find out that this is how a main bearing arrangement look for this kind of turbine. This is where the hop will be sort of connected, and this is where the main bearing is sitting. You can also sort of find that a good representation or a typical main bearing will be looking something like this. So it's basically 1 meter across. The inner opening is 0.8 meters. It has a weight of about sort of 900 kilograms, and you can sort of read off the specification of the bearings from the manufacturers. And knowing this information, you might be able to sort of try to run the game of saying, can we now predict what the life should be? And in order to do that, in Hyperwind, we do what we call aeroelastic simulation representations, or we make an aeroelastic model representing the turbine, but we also need to represent the drivetrain. And you can kind of see this is a very simplified representation of that. So basically, you should imagine that the rotor blade or the rotor plane is connected here at the hop point. Then the hop is connected with a beam to the position where the main bearing is sitting, and then the main bearing is just going into the gearbox, going into the connection between gearbox and generator, and this is where we have the generator, let's say, position sitting. And all of this is then supported by, let's just say, 2 beams connected to the tower, which is also represented by beams. And this is what we do when we do aeroelastic simulations. Then we have a representation of how the rotor is interacting with the, let's say, with the wind, with the turbulent wind profile. And then we can simulate for 10 minutes what are all the loads, the mechanical loads ending up in this system. Of course, we need to sort of put a lot of input parameters to such a simulation. And what we usually do is that we specify sort of the load cases. And 1.2 is read from the IC standards as being sort of just normal operation. Basically, we're stepping up the wind speed from 4 to 26 meters. We actually specify that this turbine is sitting on a monopile because it's an offshore wind farm. So mean sea level is 12 meters. The significant wave height is 1 meter. The wave period of the water of the water waves is 10 seconds. We are just running normal turbulence in the wind specification, and we also say that this is normal sea state. And then by doing all this, we can actually simulate what are the loads coming into the bearing, and based on the radial and the actual loads, we are sort of capable of calculating what is the bearing loads based on specifications of that specific bearing coming from the manufacturer. So what we would kind of see typically is as function of the wind speed. So you can kind of see what is the rotor speed. This is just reflecting that as we go from the cut-in wind speed to sort of rated wind speed, the rotation speed is coming up. We are reaching a rated rotation speed, and this is also where we have rated power production from the turbine. We can read off the radial force on the bearing, and we can also read off the axial force. So the axial force is kind of how much force is pressing sort of backwards into the drivetrain, you might say. And that is just basically a replicate of the thrust force of the turbine rotor. So you can kind of see this is coming up as we reach rated wind speed. We reach a maximum as the pitch system is starting to pitch and reduce the input power to the shaft. This is coming down at higher wind speeds. And if we now sum up the radial forces, the axial forces from these two curves, we can actually get sort of what is the equivalent forces on that bearing. And basically, then we can sum up what are those forces at the different wind speeds if we use sort of a Weibull distribution to get how many hours a year do we have a wind speed of 5 meters per second, 10, 15, 20, and so forth, and we integrate the whole thing. At the end of the life, you have to sort of sum up all these, let's say, contributions to the bearing life. And just to give you a feeling of the result of running this kind of exercise, we actually, for this case, get a bearing life of 122 years. And you might say, that's long, right? Because many of you probably know that according to the IC standards, we are designing offshore turbines with a design life of 25 years. But one of the things is that this L10 bearing life is, let's say, very crude. And if you go into bearing manufacturer specifications, they are actually prescribing that you need to sort of look into what are the temperatures of those bearing under operations, because that is reflecting what is the viscosity of the lubricants, and also what is the cleanliness of your lubricants. So this is something we will actually say expand on in this project as further work, because you can kind of say that 122-year lifetime is very long, and maybe we need to sort of see if we can sort of get it a bit more realistic. And this is what we will try to do by reading the SCADA data from the Teesside wind farm and try to represent what is the temperatures actually. But we will also look into the wind conditions, let's say, different from the very idealized IC inputs that we use for air elastic codes. I'm just showing you here a results that some of my colleagues have done previously. So Laura Skröder here and Nikolai, who is the lead of the Hyperwind project, is involved. They tried for another wind farm to calculate the main bearing life. So you sort of see the L10, but now it's normalized. So they don't really tell you if they got 122 years or if it's 25 years plus minus. But what you kind of see here is that if you run the air elastic code and you try to calculate the bearing life, you will see that bearing life is reduced at the edge of the wind farm according to this kind of simulation. And this is just reflecting that basically the shadowing effect from the front row to the rows inside this wind farm here, the primary wind direction is kind of coming from here in this case and coming from here. So you can kind of see that there is actually less wind in the center of such a wind farm because the front row is actually harvesting some of the energy. And this is also making the life of the bearings inside the wind farm should last longer than they should at the edge. And of course, this is kind of giving sort of inspiration to future wind farm controllers, if they should actually take into account that the set points of different rows in the wind farm might be set differently in order to either run down some turbines faster than others, or if one has a problem with one turbine, would it be possible to change, let's say, the settings of the wind farm to mitigate that we have an issue? And this might be a way of gaining time to make sure that a ship can come and replace a main bearing on one of these wind farms. So just to sort of give you a feeling of the future work, we will be also addressing the main bearing of the 15 megawatt, as well as actually the high-speed bearings of the Teesside machines. And finally, we also collaborate with IPRI, and I think we'll get a presentation, or we will get a presentation here. How do we couple all this with potentially grid faults? So if we have faults on the grid, low voltage ride-through situations, will that feed back into our drivetrains and actually take away some life from these bearings? Okay, I think these are the words from now, or from me. Yeah, so we should acknowledge the Horizon 2020 program for funding this. And if you have further questions, the Hyperwind website is there. Our emails are there, so please ask. And I guess now I'll pass it on to Yixiao.
Yes, now I will take the control. Thank you so much, Asger, by the way.
Yeah, thanks.
For the presentation. Because we are running out of time, so I'm trying to skip too much details. Yeah, so from the last presentation, Asger has given us a very nice talk about the Hyperwind project. If you can see my screen, and now I want to give some insights from the EPRI perspective to understand what we are doing in this project and how we collaborate with our partners to work on the offshore wind energy. And we are focusing on the analysis of the grid disturbance effects on wind turbine mechanical components, and it is based on inter-mechanical modeling framework. So before we go into the details, I want to take one step back to answer why are we interested in the grid events? Why are we interested in the impact of the disturbance on the mechanical components? So here's a picture to show you what the grid-connected wind turbine system looks like. We have the wind turbine, which is connected by the electrical cable to the power grid. And in this way, we're able to integrate the wind power sources into the transmission system. And because of connection between turbine system and also the power grid, the wind turbine will experience some grid events disturbance, like the local voltage problem, reduce the power quality, and also it will integrate the normal power supply in extreme conditions, lead to electrical and mechanical failures, and result in the system collapse. So I'm trying to skip the details of the voltage stack here, but I want to stress is the disconnection of the wind generation in the grid event disturbance is not preferred because it will lead to the local voltage problems and reduce the power quality. So the wind turbine is no longer expected to be disconnected in the event of the grid disturbance. It is very important to keep the wind generation continue operating. This is the reason that why we need the analysis. We need to understand how the turbine will respond to the grid disturbance, how such an event will influence the wind turbine reliability. So this is it. And in the next slides, I want to show you how we are trying to figure out this problem. So for this purpose, EPRI has proposed a numerical framework to analyze such a grid event disturbance on the mechanical components of the wind turbine. So in this framework, we have turbine component, including the aerodynamic, the structure, and also electrical component. And then they communicate with the wind turbine controllers. And the electrical components, like the generator, is connected to the electrical grid. DTU has been working on the modeling of the structure with a particular focus on the drive chain and its degradation model, as Asper introduced in his presentation. And EPRI is working on the electrical component, such as generator and also the electrical grid modeling. In the later stage, the structural model from DTU will get integrated in this numerical framework to finalize our analysis. And imagine there's a disturbance happening to the grid. We will see some variation of the voltage and the frequency out of the electrical grid because of the interconnection between the grid and the wind turbine components. So it will propagate into the mechanical dynamics of the wind turbine. So we will see some torque changes in the drive chain at that. It would be also very interesting to see how the turbine responds to different grid events and how we can quantify such impact on the mechanical components, and also how we can take into account such an influence in the future reliability design. So this is a numerical model. Of course, we need some validations. Our partner EDF also provided an offshore wind farm SCADA data from T-side farm to help us to understand the simulation results and also validate the numerical model. So this is how EPRI worked together with DTU and EDF in this work package to contribute to offshore wind energy in Europe. And of course, we have other partners from different universities and organizations, which will also provide us very solid support in the later phase if needed. So now I want to make use of the rest of my slides to dive into EPRI's vision on future wind collaboration opportunities in Europe. As you might have heard, that the Dutch government just announced that they designated 3 new offshore wind farm sites, and the total capacity will double to 21 gigawatts by 2030. You might be also curious, how many offshore wind turbines will be built in the future. If you believe the outlook made by the global wind energy concerns, it says 940 gigawatts in the Europe. By 2050, we will expect 940 gigawatts capacity of offshore wind turbines installed in the European water. We will see a big revolution in the wind industry in terms of larger scale structures of the turbine, more flexible and longer blade, more intelligent control and health monitoring algorithm. We even have a floating platform for deep water wind exploitation. So all those predictions are based on the new technology to make the offshore wind more cost effective. So this is what I can imagine. How to do that? First, we are towards enhanced reliability, analytics, and disturbance resilient design. So Roger has given some insights on the turbine reliability and the performance wind program. And in the future, of course, we will have more powerful tool to help us to understand how the reliability and the performance of the offshore wind turbine will be influenced by the offshore environmental disturbance, and what we can do to take into account such an impact in the reliability. And also, we are looking into the turbine control and health monitoring technologies, because the large-scale offshore wind turbine will experience more severe aero and hydrodynamic loading, and they are more prone to suffer from faults and failure. So this means that we need a more intelligent turbine control and health monitoring to reduce the load, maximize power, and detect the failure in the early stage. So first, we will have better measurements, like LiDAR. So LiDAR is also interesting for wind energy, because what we can do for LiDAR, with LiDAR, we can measure the upcoming wind. So if there is a gust in front of the turbine, so it means that we can already anticipate it based on the LiDAR measurement and take it into account in the control system design. So we will have a lower loading and bigger wind. And the second is a data-driven algorithm. So we were talking a lot about the data today. And in my vision, we need a model to build up the algorithm. So we make the model with everything we know based on the first principles constructed from reality. So we call it a physics based on. For those things that we don't know, we are trying to explore them from data. And then we combine both of them in the model in a certain model structure. We can use it for control and health monitoring algorithm. So building the algorithm, what we always do is to go back to the reality, go back to the real systems, the real wind farm, and the real wind turbines. Because I think we can find something from the real data. And I would like to stress here is the data-driven technique is much more than just a machine learning, because it combines the measurements, the first principles, that everything we know, and also the model structures for the control algorithm. And then finally, there are lots of new technologies coming in. For instance, we have digital twins, we have floating type of wind turbine, we have vertical axis wind turbines. Also, we have robotics, like the drone. We can use them to measure the flow in the wind field. But this is only part of my story, because if we look beyond the state of the art, we are also interested in offshore grid innovation, as the offshore wind industry is facing challenges around offshore transmission, including many unexpected cable damages, the incremental cost of offshore grid, and the delays. The second challenge is around the lack of centralized planning and coordination, which leads to incremental transmission cost, project development cost, and the interconnection delays. I believe some of my colleagues would be able to give more insights on the offshore grid innovation. We need a high voltage dynamic cable technology for the floating wind turbine application, because the floating wind actually shows more extra 6 degree of freedom of low frequency dynamics compared to the bottom fixed wind turbine. Such dynamics will introduce unexpected fatigue cracking of the cable. So if we could have better design of the offshore grid with the help of the robotics and digital twins, the turbine can be placed in the deeper water to harvest the floating wind. Instead of putting all the turbine together in the shallow water, we can also explore the location where it is very difficult, very hard to put the turbine on. So better understanding of the offshore grid, better understanding of the control and the health monitoring, the turbine can be bigger. So let's finally go to a couple of take-home messages. So we will have enhanced and reliability design for the next generation wind turbine. We'll have a more intelligent turbine control and health monitoring, and we are also interested in advanced offshore grid technology for the future offshore transmission. But this is still part of my imagination. What we can do, because we need a close collaboration. We need a close collaboration with people from different backgrounds to bring all those new elements together to push the frontiers of the future offshore wind energy. So all those together, it will become reality. So I consider this as a wind energy in the future. And I end up here.
Okay, thanks very much, Yichao. Maybe just to finish it out, I wanted to thank everybody for coming. I know we're a minute or two over. It's Eamon here from EPRI, and I know slide, yeah, camera's not working for some reason, but I just wanted to mention as we close that there's a lot of opportunities to do the likes of work that we're doing through Hyperwind, through the forthcoming calls that are there. Forthcoming calls that are there in the existing Horizon Europe work program. So already discussions happening on some of those across wind, hydro. We didn't talk about it today. CSP, and more generally across the renewable energy value chain. There's a pretty good call out there. Interesting, funny name, but interesting call. And then we've seen that the future work program for 2023-2024 contains a lot more along the lines of what we've heard before: the need for digitalization, the need for improved models, to bring down the cost and improve reliability of wind and solar power as they continue to get rolled out. So we look forward to opportunities to collaborate with you all, hopefully in the not too distant future. Appreciate the opportunity to do that, for your attendance today, and thank you for being engaged. Look forward to talking to you again. Thank you very much.
Everybody.
Thank you.